to understand the process that modulates that ice albedo feedback, right? The process that controls or prevents the Earth from just totally icing over or losing all of its ice and never getting any back. To understand that process, like I said before, we're going to have to dive in to another climate record that's got a higher resolution. So now we're going to dive into a climate record that's less than 1 million years old. Okay, so here we've got a greater than 60 million year duration of this climate record. The one we're going to look at next is just like a little line, right? Just barely even visible on this plot here. Less than 1 million years. Okay, here it is. This is our new climate record. So the first thing you'll notice is that it's a squiggly blue line here, and this squiggly blue line is plotting global delta 18O of seawater again in units of per mil. So it's the same quantity that we're plotting compared to the last one, but notice here in the x-axis, our time axis is much smaller. Now we're looking at an 800,000 year record. So age in Ka, that stands for kilo annums, or thousands of years. So 800,000 years is the length of this record. Less than 1 million years. Okay, so what is this squiggly blue line? This squiggly blue line, as it says on the axis here, is the delta 18O value of global seawater, SW. Okay, how do we know that? Well, similar to the previous plot, this diagram was constructed using the shells of planktonic animals like foraminifera. So it's essentially the same kind of plot, but the researchers in this study used additional geochemical techniques to remove the effect of local temperature water. So recall that the benthic forams recorded not only the total volume of ice on Earth, but also the local temperature of the water that they lived in, where colder waters made foram shells have lower values. So these researchers did additional techniques that we don't need to go into to remove the effects of that local signal of the temperature of seawater. And so by doing that additional treatment, this plot here is the oxygen isotope record of foram shells, planktonic foram shells, that should be recording only the variations in ice on Earth's continent. So only the variation in continental ice through time. And so that's what we see is this wiggly line. And you see that there's sort of a pattern, sort of a cyclicity to the wiggles here. Recall that the higher the delta 18O value the planktonic foram shells show, the greater the volume of ice. So just like in the last plot, the axis here is flipped with larger values going down and smaller values going up. And the reason for that flipping is that it makes more sense because a downturn on this diagram with the axis flipped represents colder temperatures. So that's why these axes are flipped. Okay, so you might notice these faint pink and white bands on this plot. And these faint pink and white bands represent times in the last 800,000 years when Earth was either extensively glaciated or in an interglacial period. Okay, so you can see here on the very edge of the axis, on the x-axis, right near 0, right near today, we're in a pink band. This is an interglacial period, right? We have relatively less ice on the surface of the Earth than we did 20,000 years ago during the last glacial maximum. So these white strips represent periods where there was extensive glaciation, and the pink strips represent periods where there was less glaciation. Again, if you just think of this axis as being sort of temperature, these points are all relatively high temperature. These points are all relatively low temperature, right? Colder, more ice, warmer, less ice. Colder, more ice, warmer, less ice. So that's how to read this plot here. But so you'll notice that there's this peaked and troughed, sort of cyclicity to this plot. So we want to explore what process causes this cyclicity in the global volume of sea ice. What makes that happen? The ice albedo feedback is modulated by variations in Earth's orbit around the sun. We also refer to these as orbital cycles. And so there are three different parts of Earth's orbit around the sun that change through time. Those three parts are called eccentricity, obliquity, or precession. Okay, so each one of these has its own effect on Earth's climate, but first let's explain what each one is. So the eccentricity is how circular or elliptical Earth's orbit around the sun is. So the Earth goes around the sun once a year, and we think of this orbit as being circular. We learned in our first lab that it's not quite circular, that the Earth has a point in its orbit where it's close to the sun, called the perihelion, and a point in its orbit where it's far away from the sun, called its aphelion. Eccentricity changes the size of the difference, the magnitude of the difference between those 2 points in Earth's orbit, its perihelion and its aphelion. So it controls how circular or elliptical Earth's orbit is. So I have greatly exaggerated just how much Earth's orbit around the sun changes to make this point. But basically, if we imagine that over here is the perihelion, where the Earth is always closer to the sun over on this side of its orbit, and this side represents the aphelion, where it's far away. You can see that as the Earth's orbit gets more elliptical, it's the difference between the perihelion and the aphelion becomes much more pronounced. So this is called eccentricity, and eccentricity varies on cycles of 100,000 years. Okay, obliquity, which is also sometimes called tilt, is how tilted Earth's axis of rotation is. Okay, so again, we remember from our lab a few weeks ago that Earth's axis of rotation is tilted, and today that tilt is 23.5 degrees, so 23.5 degrees. 23.5 degrees. But the magnitude of this tilt changes through time. It fluctuates between about 24.5 and 22.1 degrees. So again, I've greatly exaggerated this here just to make the point, but so Earth's axis of rotation moves back and forth between 22.1 degrees and 24.5 degrees. Currently we're at 23.5 degrees. Okay, and obliquity, the tilt of Earth's axis of rotation, varies on an order of, it varies at 41,000 years cycles. Finally, precession is, you can think of as sort of the wobble of Earth's axis of rotation. So if you can picture spinning a top, when a top is spinning in place, right, the part that you spin and hold, that axis of rotation rotates around like this as the whole thing is spinning, right? So that's just like the precession of Earth's rotation around the Earth. So what precession controls is the direction that the northern hemisphere is pointed in throughout Earth's orbit. And so that varies. Sometimes Earth's axis of rotation is pointing off towards the North Star, which is where it points towards today, and then sometimes it's pointing towards the star Vega. So Earth's precession varies on 23,000 year cycles. So how do each of these orbital parameters affect the growth or shrinking of ice? Okay, so remember that ice can only accumulate when the mean annual temperature at the poles is low. And so each one of these different orbital parameters affects the mean annual temperature of the Earth, especially at the poles. For example, the obliquity of Earth's rotation, right? So how tilted its axis is. When the obliquity is high, when it's at 24.5 degrees, then that means that during the summer, the northern hemisphere is pointed more directly towards the sun. That means it receives more solar radiation and it's going to have higher annual temperatures, mean annual temperatures. When obliquity is low, when its axis is rotated back more this way towards 22.1 degrees, the northern hemisphere is less tilted towards the sun, and so it receives less solar radiation. So that makes its mean annual temperature lower at the poles. Similarly, the precession of Earth's orbit, this controls where, at what point in Earth's orbit, the northern hemisphere is pointed towards the sun, right? So we recall from our lab that in the northern hemisphere, the northern hemisphere is pointed towards the sun at its aphelion, right? At the point when it's actually furthest away from the sun. But because precession changes on a much shorter time scale, that means that there can be times of the Earth's orbit when the northern hemisphere is actually pointed towards the sun when it's at the perihelion. So that means that it would get more solar radiation because it's closer to the sun and it's pointing towards the sun. Because all three of these things vary on different timescales, that means that inevitably they will line up in such a way to either cause very, very warm summers in the northern hemisphere or very, very cold summers in the northern hemisphere. So because of the changes in obliquity and precession that are so much shorter than the changes in eccentricity, eventually you will have a situation where, for instance, the obliquity is high, 24.5 degrees, and the obliquity is high, 24.5 degrees, and the northern hemisphere is pointed towards the sun at its perihelion. Those two things combined will give very, very warm annual temperatures in the poles. In contrast, it's also going to line up that at times the obliquity will be very, very low, and that the northern hemisphere will be pointed towards the sun at its aphelion, right, when it's the furthest away from the sun. That will give very, very mild summers with relatively low temperatures, and that allows ice to persist and to even grow. So it's these orbital cycles that combine to either kick off the ice albedo freezing effect or to kick off the ice albedo melting effect. It's the orbital cycles that control the growth and the retreat of glaciers on the hundreds of thousands of year time scale. The effect of each one of these orbital parameters on northern hemisphere summer insolation, or how much solar radiation is absorbed by the northern hemisphere, can be calculated. And to give you an idea of how that works, sort of just show schematically here. So each one of the cycles that we've talked about varies on different time scales. Eccentricity, the ellipticity or circularity of Earth's orbit around the sun, varies on 100,000 year cycles. So that means that on one 100,000 year cycle, Earth's orbit goes from being very circular to being very elliptical back to being very circular. So one cycle is 100,000 years. The second cycle would be shown like this. That's the eccentricity. the obliquity of Earth's rotation, right, how tilted its axis is, varies on 41,000 year cycles. So 41,000 year cycles. So each cycle of obliquity takes 41,000 years. That means that its axis goes from being tilted at 22.1 degrees to 24.5 degrees and back to 22.1 degrees on a 41,000 year cycle. And finally, the precession, right, the wobble of Earth's axis, cycles on 23,000 year time periods. So each wobble of Earth's axis takes 23,000 years. So the total effect of summer insolation in the northern hemisphere can be calculated by taking these three curves and sort of adding them together, because each one of them is going to affect solar insolation in the northern hemisphere in a different way. So you can take, when you take each one of these different curves and add them all together, you'll end up having a squiggly line that has curves, you know, like curves superimposed on other curves. So there will be a broader cycle of 100,000 years, but there will be shorter squiggles kind of superimposed on that. So this effect of each signal is harder to see because all three are working together simultaneously at different time scales. And so this figure shows the same global oxygen isotope composition of seawater curve from before, now compared to this black line, which is the calculated summer insolation in the northern hemisphere at 65 degrees north on June 21st, based on the effects of each one of those three orbital parameters all stacked together. Right, so what you can see is this, like I said, this kind of squiggly line with multiple different kinds of wiggles, right? You can see the sort of minimum or the maximum and minimum values are extreme here, and then they're small here, right? So there's a longer 100,000 year cycle that's at work. There's a shorter 41,000 year cycle, and then superimposed on that is the shortest 23,000 year cycle. And so what this means is that there are periods, like long periods in Earth's orbital parameters, where the summer insolation is pretty mild. So what you'll notice is that the white bands that represent glaciations usually take place where there's less wiggle, right, between highs and lows of summer insolation. So here there's sort of less of a difference between the high and low of summer insolation. This glaciation is probably caused by this very, very low summer insolation here, and then it didn't get quite high enough to really melt everything and stayed pretty low. And then over here in this pink band, we see that summer insolation was quite high, right? So the northern hemisphere received a lot of sunlight and all those glaciers melted, right? So the oxygen isotopes show that, boom, there goes the ice, disappears, it's not very much ice, and then it comes back. So each one of these pink and white bands are showing the times of glaciation and deglaciation. So a technique called spectral analysis has been used to quantify the correlation between these two curves. So how well the variation in this curve explains the variations seen in this curve. And spectral analysis reveals that the orbital signals of Earth's orbit have a very strong effect on the volume of global continental ice on Earth through time. I just want to add a few details, just some comments about this plot for the keen observers who might have noticed some discrepancies. So one, There are occasional mismatches between the solar insolation and the ice curve, and some of them are caused simply by sort of a shortcut taken by some scientists. So because this is actually sort of fairly old science, this was first proposed in the 1800s by a Serbian scientist named Milutin Milankovic. So in the over 100 years since that time, we've had a lot of time to work on this. And so you'll notice that this is the solar insolation on June 21st at a specific latitude. It's simpler to calculate that than it is to calculate an integrated solar radiation over the entire surface area of the Northern Hemisphere and also over a longer period of time, like over the whole summer. So because that's computationally more challenging for the purposes of like producing a figure, like so this figure is from a paper from 2015, fairly recently, and the fact that these two things, the oxygen isotope record of the oceans and orbital cycles vary together, was not the focus of that paper, right? So here it was appropriate to use the kind of shortcut, the easier computation, just to show graphically something that we kind of already know to be true. So that's one thing that, that you might notice. There are also some mismatches between the orbital cycles and the oxygen isotope record of sea ice that have more geologic causes, but we're not going to get into them. They're sort of beyond the scope of this class. But again, coming back to the plot, some of you might have noticed that the delta 18O values are very different on this plot compared to the other plot that we've been looking at of the benthic forams. So here, back to the plot of the benthic forams from Zakos and others in 2008. You can see that the oxygen, the delta 18O values in forams are down here on average at about 4 per mil. And here, over the last 800,000 years, we only see them varying around 0, right? So I just want to say that, again, the researchers who produced this paper, they took the median value over the last 800,000 years and set that value at 0 just for the purpose of making this plot. So there's nothing fishy going on. It's just some tweaks to the figure that were made sort of for the purpose of more easily communicating the information in the publication itself. Finally, just to bring it all back, the reason that that previous diagram plots the summer insolation in the Northern Hemisphere is, again, because once ice does get established on the Northern Hemisphere, because there's more real estate, right, more land for ice to occupy, the Northern Hemisphere solar insolation really does control the extent of global ice, because there's more space for ice to accumulate in the Northern Hemisphere than there is in the Southern Hemisphere. So that's why everything is sort of, compared to the Northern Hemisphere for all this glacial, interglacial stuff. All right, just to recap, so far we've talked about long-term climate change, how it's caused by changes in the carbon cycle. So this was our discussion of chemical weathering of the Tibetan Plateau causing long-term drawdown in CO2 from the atmosphere. And we've been talking about the controls of orbital cycles on continental glaciation, which are controlled on sort of tens of thousands to 100,000 year timescale by the changes in the Earth's orbital parameters. Moving forward, we'll discuss how CO2 varies in the atmosphere during these glacial interglacial cycles. And we'll also begin talking about recent climate and the effects of climate change and human activity and how that affects climate change. As you can hear, my cat has very strong opinions on this, and you'll be hearing all from Leo next week.